Well, let me start by thanking Professor Lee for his kind invitation to come and lecture here. And let me say thank you to KAIST for the pleasant working conditions. So, this talk is about smooth projective algebraic surfaces. Right now, let's not worry about what field we're working over. The field could be arbitrary, but sometimes we'll talk about specific examples. And so the question is, given an algebraic curve, we have an intersection theory on the surface. How negative can the self-intersection be? And so that's the general idea. In fact, it can be arbitrarily negative unless we make some conditions. And so to allow us to be more specific, I want to look at a test case. So instead of letting x be an arbitrary algebraic surface, let's let x be a blow-up of points in P2. And let's say the points are distinct. So to denote how many points I'm blowing up, I'll use a subscript s. But the points could be special, they could be general. We don't know anything about the points at this stage. And so let me remind you about the intersection theory. This will be important through all of my talks. So the divisor class group, well, every divisor is linearly equivalent to a unique expression of the following form. So I'll write that this way. Twiddle means linear equivalence. Some multiple of the class of a line minus some multiples of the blow-ups of the points. So L is the proper transform of a line. And EI is the blow-up of the ith point. And so the first thing to notice is that the intersections of the blow-ups themselves are negative. So there are curves of negative self-intersection. In general, the intersection theory works like this. The line intersects a blow-up 0 times because you can always pick a line that avoids the class of the blow-up. And the intersection of the blow-ups of distinct points, they don't meet. And so this is going to be 0. And the self-intersection, of course, L squared, 2 lines meet in a single point. So that gives us the intersection theory. As an example, here we have x, and here we have P2. Let's take a line through 3 points. If you blow up the points, you get E1, E2, and E3. That's the inverse image of the point. And then the proper transform of the line C that's linearly equivalent to a line, and I can subtract off the blow-ups of the 3 points. And so we can compute the self-intersection. That's just going to be the self-intersection and then using linearity we can compute, we get, these are orthogonal, so it's going to be 1 minus 3. So here we get a curve of negative intersection. And you can see that we can take more points on this line. So in fact, if I take S points on C, C twiddle squared, this is just going to be L minus E1 minus ES squared. This will be 1 minus S, so this is going to be arbitrarily negative. Just take more and more points. So that might make this question, how negative can the self-intersection be, silly. It can be arbitrarily negative. But to do this, we had to take more and more points. And so the question is, if you fix the surface, how negative can it be on a single surface? Rather than taking different surfaces, getting more and more negative curves, what about fixing the surface? How negative can it be? So suppose we fix the surface. How negative can the self-intersection be? Well, again, if you fix the surface, here I have a negative 2. Suppose I take a multiple of this. Well, if I take a multiple of this and then take the self-intersection, this is going to be negative 2 times m squared. So again, it's going to be arbitrarily negative. So what I'm interested in is for reduced curves. The interesting question is, how negative can the self-intersection be for a reduced curve on a fixed surface? And so here is a conjecture. This is an old conjecture. Nobody knows who exactly this conjecture is due to. It goes back into the mists of time. So this is called the bounded negativity conjecture. There are two versions, and I'll state both of them. Here's the first one. I heard this conjecture in about 1980 from my advisor, and talking with an Italian algebraic geometer, Ciro Ciliberto. Ciliberto says that he heard it from his advisor, who heard it from his advisor, who was Enriquez. So if you know any of the history of algebraic geometry, Enriquez was an important algebraic geometry in the first half of the 1900s. And we don't know who Enriquez heard it from. Maybe it was his question. So it's somewhere on the order of 100 years old. And it's still open. So for simplicity, it's a little complicated to say the most general version. So for simplicity, I'm just going to assume X is a rational surface obtained by blowing up points of P2. You don't have to restrict it to that case, but then you have to be careful. So I'm going to restrict it to that case. Given X sub S, there is an integer B sub S greater than 0 such that C squared is greater than or equal to minus B sub S. So this is a lower bound for the self-intersection for all reduced and irreducible curves C on the surface. So, well, one question might be, okay, so let me mention a couple of examples. You could see that to get a negative self-intersection here, the points were special. Those points were collinear. Suppose the points are generic. So suppose the S points are generic. Well, it's an open question in that case, but there's a conjecture. The B and C is open. So I'll call this B and C1 for bounded negativity conjecture. It's open, but there is a conjecture. In fact, let me state another conjecture called the SHGH conjecture. So the SHGH conjecture says something in this exact situation. It says if there are various versions of this also. So they're all equivalent. Here's one version of it. If C, X has to be a blow up at generic points. If C is a curve on a blow up of P2 at generic points, where C is reduced and irreducible, then C squared is greater than or equal to the arithmetic genus of the curve minus 1. And the arithmetic genus of the curve is always greater than or equal to 0. And it's equal to 0 if and only if the curve is a smooth rational curve. And so what this says is, this is a conjecture. So it's not known to be true. And it's a lot of people have worked on this for the last 40 years. It would be, any progress on it would be very exciting. So as a corollary, assuming the conjecture C squared less than 0 on a blow up at S generic points implies that C squared is negative 1 and C is a smooth rational curve. So in algebraic geometry language, this is an exceptional divisor, an exceptional curve.
So is there some known result for very small s?
Yes, and so that's the next thing, my next example. So this was example 1. Example 2, if S is less than or equal to 9, the bounded negativity conjecture is true. The reason that it's true for S less than or equal to 9 is because the anti-canonical divisor is effective. So S less than or equal to 9 implies that the anti-canonical divisor can be written this way. there's always a cubic through 9 points. And so the proper the transform of the cubic through the 9 points gives you an effective divisor linearly equivalent to minus k. So minus k is effective. And now we have the adjunction formula. It's the genus formula. So this is a very elementary fact, and yet it's maybe the strongest fact that's known. So the strongest fact that's known is something that you would figure out in the first few weeks of a course on algebraic geometry. And there's not much progress after that. So this is a hard problem. So this is also called adjunction. But it's the genus formula. So what it says is, if C is reduced and irreducible, C squared plus CK is equal to twice the arithmetic genus of the curve minus 2. And so now we can just do a little arithmetic. Let's write C squared is equal to twice the arithmetic genus minus 2 minus C sub k. Now there are two cases. Suppose that this C meets minus k non-negatively. Well, this term is non-negative. This term, by assumption, is non-negative. So C squared is greater than or equal to negative 2 in this case. The other possibility is that C intersects minus k negatively. But this is an effective divisor. So this means that C is a fixed component of the linear system. There are only finitely many fixed components. And so there's only a finite number of self-intersections. And so you just take the minimum of minus 2 in that finite number, and that's the minimum on that surface. So there are only finitely many possible values of C squared. Well, this is a cubic, basically. It's coming from a cubic through 9 points, so you can analyze it. What is the worst case? The worst case of a curve, which is a component of minus k, is, well, it could be a line through 9 points. It could be a conic through 9 points, a cubic through 9 points. But the worst case is the line. So, in fact, C squared is less than or equal to what happens if you take the line through 9 points, and so that's negative 8. It can't be less than negative 8. It might not be negative 8 because not every surface will have a line through the 9 points. But there's another version. All that we really require is that C is a reduced curve. So suppose instead of looking at irreducible reduced curves, maybe the curves are just reduced. What can you say in that case? So that's a second version. It says there is an integer depending on the surface greater than 0 such that C squared is greater than or equal to minus that integer. So this is a conjecture. I want to emphasize. The self-intersections of reduced curves is also bounded below. So reduced curves are bounded below, and in fact these two are equivalent. The first and second conjectures are equivalent. If you can prove one, you can prove the other. So if you have a bound on the self-intersections of reduced curves, every reduced irreducible curve is among those. So given a bound on the reduced curves, we can take the bound for the irreducible ones to be the same bound. It will suffice. It's not the optimal bound, but it will be enough. And this one is a little harder to show. Given a bound on the prime divisors, the reduced irreducible curves, we can take capital B to be S times little b. And the S is it's one less than the Picard number of the surface. So this comes from, the proof comes from Zariski decompositions. If you have a divisor that has a very negative self-intersection, it'll have a Zariski decomposition, and you look at the negative part of the Zariski decomposition, that will be orthogonal to the positive part, so it's in a rank S subspace of the divisor class group. And anyway, it would take a little while to go through that argument, but it's coming from Zariski decompositions. But let's look at a couple more examples. So we know that BNC1 is true if you take at most 9 points. So that means that BNC2 is true for S less than or equal to 9. What is the worst case example? How negative can you get? So let me preface this by saying I don't know. So maybe you can figure out what the absolute most negative example is. But I'll give you two possibilities. I think these are probably optimal, but I don't have a proof at the moment. So let's take 8 points on a line and 1 point off. And the curve that I want is the proper transform. We're going to blow up these 8 points and this point. And let's take the proper transform of this curve, which has degree 9. It's got 8 lines, the lines through the points on this horizontal line and through this point, together with the line through these points. And if you take so this is C. C tilde is the proper transform, and it's not hard to work out that this is negative 15. At least that's the most negative example I could come up with. Well, that's the most negative example in general, but suppose the field has characteristic 2. So this problem has a strong combinatorial component. And in fact, problems related to negativity are also related to problems in number theory, which I'll talk a little bit about later. If the ground field has characteristic 2, then it contains the Fano plane. So let's look at the Fano plane. The Fano plane is basically just the points whose coordinates are always zeros and ones. There's 7 points where each point has coordinates only zeros and ones. Here are 6 of them. Oh, this is x equals 0. This is y equals 0. Oh no, I want that to be z equals 0. This is y equals 0. Here are 6 of the, oh no, this is 7 points. 1, 2, 3, 4, 5, 6, 7. There are also 7 lines. Here's an additional line. In characteristic 2, that circle is a line. We get 2 more points to blow up. And so I'll blow up a point here and a point here. So we're working over the field Z mod 2. Well, the algebraic closure of Z mod 2, because I need 2 extra points. The proper transform, if you work this out, has self-intersection negative 16. It's a union of the proper transforms of the 7 lines. And so negative 16 is the absolute minimum I've been able to come up with over any field. But it might be possible to do better. I'm not sure.
That number is related to the 2 times the arithmetic genius?
I'm not sure. Yeah, it's just what it is. I don't know if it'd be nice to explain it somehow, but I don't have a good explanation for it. So in characteristic 0, I don't think you can get negative 16. So if there's an explanation that involves some fundamental invariance, it would be surprising that it only works in characteristic 2. But so here's a homework exercise. Beat my example. Come up with a negative 17 or something like that. All right, now I want to switch gears a little bit. We don't have to do what I'm going to do, but it simplifies the discussion. So for simplicity, we don't really need to blow anything up. You can see that I'm doing the construction on P2, and the blowing up, we can see what's going to happen. So let's just do everything in P2. So given a curve in P2, and given some points, instead of blowing up the points and taking the proper transform, let's do the computation on P2. So what I'll do is I'll define Q of C with respect to the points. The Q just stands for quadratic. I'm going to be defining a quadratic operator. It's basically the self-intersection of the proper transform of the curve after you blow up. So the quadratic operator is just going to be the degree of the curve. So here, for example, this was a curve of degree 9, and C squared is going to be the degree squared, and then we have 8 points of multiplicity 2 and 1 point of multiplicity 8. And so if you work this out, if I did it correctly, it's negative 15. So I want to just do that here. So we take the degree of the curve squared minus the multiplicity of the curve at each of the points squared. And so here, for example, I have a point of multiplicity 1. Here's a point of multiplicity 0 because it's not on the curve. Here's a point of multiplicity 2. So this is the same thing as what we were doing, except we don't have to blow up the points. Now, an advantage here is that what I can do is I can pick a curve that I think will give me a very negative value, and then I can pick the points on that curve to try to minimize the value, make it as negative as possible. So here's an example. We already did this one. Suppose we have a line, and the points, let's pick 32 points. Obviously, if you want to make it as negative as possible, you want all the points to be on the curve. You're wasting the point if it's not on the curve. So I put all of them on the curve. And in this case, what we get is negative 31. Well, here's another example. Suppose you take a map of P1 into P2. So I want a general map of P1 into P2 of degree D. So the image of P1 under a general map of degree D is, well, it's going to be a rational curve. It's going to be rational because P1 is rational. It's going to be generically injective because it's not going to map onto itself. That would not be a general map. So it'll be degree D, plane rational curve. But because D can be bigger than 2, a conic is smooth, but higher degrees are going to be singular. It's going to have singularities. And because it's a general map, the singularities will all be nodes. And each node reduces the arithmetic genus by 1. And so the number of nodes has to be D minus 1, choose 2. So let's look at the example that we get with D equals 9. So the points I want to pick are the nodes. I'm going to pick the nodes. So that means S is the number of nodes, and the nodes are what I'm going to pick. And if you compute the intersection number, what you have is D squared, because its degree is D. Each node has multiplicity 2, so that's 2 squared, and they're D minus 1, choose 2 of them. And if I'm choosing D equals 9, this is negative 31. So here I have 2 examples. I want to think of this as a game. So usually in game theory, it's always Alice and Bob. Really A and B, but it's always Alice and Bob. So Alice and Bob have a competition. I don't know, who do you want to have? Which one, Alice or Bob, do you want to have this one? By picking the name, you're going to pick a winner or loser. You don't know yet maybe which is the winner and which is the loser. You want Alice or Bob here? I don't want to pick, because then if I pick Alice to be the loser, I'm discriminating somehow. Or if I pick Bob to be the loser, I'm discriminating somehow. You've got to pick because you don't know who the winner and losers are. Bob. Okay, so this is Bob. So this is Alice. Is Alice or Bob the winner? It's both negative 31. They're equally negative. how do you compare? If the numbers aren't equal, how do you compare? One way to compare is to divide by the number of points. So then you're computing negativity per point. And the goal is to get the negativity per point as negative as possible. So that is the H constant concept. Don't compute the negativities because they can be arbitrarily negative. Compute the negativity per point. Divide by the number of points. So this is going to be Q divided by the number of points. So in this, what Bob gets is negative 31 divided by 28. So that's the H constant for this curve and those points. Over here, the H constant for this curve and those points is oh, yes. What am I doing? 32. But 8 choose 2 is 28. That was the 28. Alice is the winner. Negative 31/28 is more negative than negative 31/32. Now, you could study this in this form, but I want to simplify it a little bit. And so I'll simplify it a little bit. Obviously, we only want to pick points which are on the curve. If you pick points that are smooth points, you're only subtracting the multiplicity of a smooth point, which is 1 squared. So you're not helping much. You're increasing the denominator by adding a smooth point and subtracting very little. So if you think about it a little bit, you'll see essentially what you're doing is you're averaging the squares of the multiplicities. If you ignore this, averaging a bunch of 1s pulls your average up typically, and we're trying to go down. So what we'll do is we'll only define the H constant for singular curves, and the points will always be the singular points of that curve. So H of C, let C be, and it's only reduced curves that I'm interested in. You can look at variations of this definition. Nobody knows what the absolute best definition would be. This is just a way to try to get intuition about the bounded negativity conjecture. So anyway, this is how I defined it. Let C be a reduced singular plane curve. H of C is going to be the curve where the points that I'm going to pick are the singular points of the curve. And so I'm going to divide by the number of singular points. So that's the H constant of the curve. And the question is, how negative can that be? The reason that we're looking at this is the following fact. We were hoping that this would be useful. So here is the fact. Well, let me introduce a little more notation just for simplicity. H of P2 will be the infimum of H of C for all reduced C in P2. So take the infimum. It might be negative infinity. Maybe there's a sequence of curves where the H constant becomes arbitrarily negative. But the fact is, if H of P2 is not negative infinity, if it's bounded below, then the bounded negativity conjecture, whichever one you like, they're equivalent. The bounded negativity conjecture for rational surfaces is true. You can study the bounded negativity conjecture for other surfaces also. And this doesn't tell you anything about those. But it,
1 and 2?
well, 1 and 2 are equivalent. Yeah, so it's both of them are true if this is true. So let me tell you some facts which are known. There's a lot which isn't known. We were thinking that we would make more progress. We've made a fair amount of progress, but this raises some interesting questions which might not be that hard to address if you have the right idea. So far, we haven't had the right idea. I mean, we've had some right ideas and we've made some progress, but well, let me tell you what I mean. So, let me introduce a little more notation. So H irreducible is the infimum for irreducible curves. Suppose you only look at irreducible curves. Reduced, of course, but also irreducible. So what's known is that the irreducible H constant is less than or equal to -2.
Oh.
Yeah, we would like to know.
There is a example.
This would be wonderful, but we don't know this. I mean, is the H constant equal to -2? We don't know. What we do know is it's less than or equal to -2. And the example is rational curves of degree D with D minus 1 choose 2 nodes. That example we looked at a minute ago. If you look at that for arbitrary D, then what you get, if I let C sub D be one of those rational curves, then the H constant goes to -2 as D goes to infinity. But it goes to -2 from above. Each one of them is bigger, let me say it this way. It's -2 plus epsilon, where epsilon is positive. And it goes to -2 in the limit. This is the best example that we've been able to come up with. We don't know any examples of an irreducible curve whose H constant is less than or equal to -2. So I'm not confident yet enough to make this a conjecture. I mean, I think of it as a conjecture, but let me make it a question. Is the irreducible H constant equal to -2? If it is, then the bound in the bounded negativity conjecture number 1 can be taken to be that 2 is this -2. We can take it to be twice the number of points. So this gives us not only this not only would imply that the bounded negativity conjecture is true, it gives us a value for the bound. This isn't an optimal value, but it suffices. So, but we don't know if this is true or not. We would just, I think if someone can find an example, then you could find a bunch of examples and make a lot of progress. But no one knows how to get to -2. And we worked on this. There was a conference in 2015 in Padova, and a bunch of very motivated people were working on it. Chiliberto, Miranda, me, Klusterman, I mean a bunch of people. And we couldn't do better than this example. And this example of the rational curve with the nodes, Kim Roe thought of it after 5 minutes. So, since we couldn't make any progress on the irreducible case, we decided to go to the opposite extreme. The opposite extreme is, instead of looking at irreducible curves, suppose you look at a curve which is totally reducible. In other words, a union of lines. What can you say about a union of lines? And we were hoping that that would give us enough flexibility. You can move the lines wherever you like. We were hoping to get very negative examples, and it turns out that doesn't happen. So let's define this is the linear H constant. The linear H constant is going to be the infimum of the values of HC, where C is a union of lines. So it turns out, let me summarize some of the facts that are known. It turns out that if K is algebraically closed but of characteristic P, then the linear H constant is negative infinity. And the reason is for each finite field, contained in the algebraic closure, take all of the lines. And let that be the curve and compute the H constant. What you get is the following. So my curve is all of the lines. So I guess I should make this Q. All of the lines over the finite field F sub Q. Then the H constant of this particular curve is there are Q squared plus Q plus 1 lines. So that's the degree of the curve, Q squared plus Q plus 1. The number of points, well, the points are dual to the line, so the number of points is also Q squared plus Q plus 1. And because it's a symmetric situation, every point has the same number of lines through it. And if you think about it, take any line. The line has Q plus 1 points on it. And so every point, you can always make a line from your given point to all the points on another line that doesn't go through the original point. In any case, every point has Q plus 1 lines through it. So the multiplicity is Q plus 1, and then you square it. And then the number of points is Q squared plus 1. And if you simplify that expression, it's negative Q. So just by taking larger and larger finite subfields, you can get arbitrarily negative H constants. So that tells us absolutely nothing. It doesn't tell us if the bounded negativity conjecture is true or false. It is interesting that the H constant can be as negative as you like. It's a little more interesting to look in characteristic 0. Suppose you just look at lines defined over the rationals. Then it's greater than or equal to -3, but we don't know the value. You can also look at it over the reals. Normally, I think of working over Q as number theory, and I think of working over the reals as analysis. It turns out, so number theory I believed was hard, and we don't have an answer. Analysis, well, I never believed it was hard exactly. I just didn't believe it was that interesting. Well, I shouldn't say that. Let me take that back. But in any case, we know the value here. It's -3. So the problem with the reals is the first thing I did when I was thinking about this was I was drawing pictures of lines. But over the reals, all the pictures you draw are going to give you nothing more negative than -3. This comes from, essentially this comes from the Euler characteristic. The Euler characteristic of the real projective plane is 1. That implies this, it turns out. In a way, I don't have time to explain it. I was going to explain it, but I'm running a little short on time. What this does, actually, is it tells you that the bound, that the linear H constant for P2 over the reals is greater than or equal to -3. To show that it's equal to -3, look at a regular polygon. The sides are the lines together with the angle bisectors. This is supposed to be a single point. If you compute the H constant for a regular n-gon, plus the lines of symmetry, then H of C sub n is equal to -3 plus epsilon, and the epsilon goes to 0 in the limit. So we know we can get down to -3 in the limit. And then this argument involving the Euler characteristic gives us that you can't go any further than -3. Well, this was just sort of interesting. The main interest is actually over the complex numbers. So what about over the complex numbers? It turns out that the linear H constant is bounded. Oh, I forgot the field. Over the complex numbers, it's bounded below by -4. And by looking at examples, it's no bigger than -225/67, which is -3.36 approximately. The reason that it's -3 here and it's more than -3 there is that here, over the reals, any line arrangement has to have some simple crossings. A real line arrangement always has at least 3 simple crossings. So for example, take 3 lines. 3 lines, any line arrangement, any non-trivial. A non-trivial real line arrangement. The trivial one is all of the lines through one point. Then you don't have any simple crossings. Suppose I try to get rid of one of the simple crossings. I'll put in another line. I created another one. There are always at least 3. And in fact, there's a better bound that says not only are there at least 3, but the more crossings you have of higher multiplicity, the more simple crossings you have. And you have so many simple crossings that this is bounded below by -3. Over the complex numbers, it turns out you can have line arrangements with no simple crossings. So the most negative example known comes from a line arrangement with no simple crossings. As soon as we realized that, the group of us studying this went on a campaign to find all of the examples of line arrangements over the complex numbers with no simple crossings. We assumed we would just go to a combinatorist and say, what is the list of all line arrangements with no simple crossings? And every combinatorist that we talked to said, well, I don't know. But I know someone who knows. Contact this combinatorist. And we contacted that combinatorist. And that one said, I don't know, but I know someone who knows. It turns out they all know somebody who knows, but none of them know. I think it's an open problem. So an open problem is to classify them. There are only 4 that I know of, and here are those 4. They're very interesting. And actually we found each one successively, and each one gave a more negative H constant. So, the first one is the trivial one. And that does not give a negative H constant. It's not interesting. The next one is called the Firma Arrangement. And if you use the usual coordinate system on P2, I'll just define the equation whose zero locus is the set of lines. Take x to the n minus y to the n, x to the n minus z to the n, and y to the n minus z to the n. Each factor is in 2 variables, so it factors into a product of lines. And what the lines look like is, these lines are a bunch of lines coming from this point. These lines are a bunch of lines coming from this point. And these are a bunch of lines coming from that point. There are n lines. Each point here is the intersection of, there are n squared points. There are n lines here and n lines here. That gives you a complete intersection of n squared points. But each point is the intersection of a line from each of the 3 sets of n lines. So what you get is n squared triple points. And then here you have a point of multiplicity n, and likewise here and here. So there are 3 n points, 3 points of multiplicity n. And if I call this curve C sub n, then h of c sub n is, you can just plug these data in. H of c sub n is -3 plus epsilon. So this gets us, it's actually no better than what we had over the reals. But there are two more. And so the two more are there's a configuration that Klein devised in 1879 consisting of the number of lines, D, is 21. And there are 21 points of multiplicity 4 and 28 points of multiplicity 3. And there are no other points where the lines cross. So every place where a line crosses another line, there are at least 3 lines that cross there, or 4. And the h constant in this case is -3 exactly. So that's a little better than you can do over the reals. There's one more example that's known. This is due to Anders Wiemann from 1896. Wiemann was a Swedish mathematician. He imitated what Klein did. And so in this case, he came up with an example with 45 lines. There are 36 points of multiplicity 5, 45 points of multiplicity 4, and 120 points of multiplicity 3. And the h constant is -225 over 67. And that is the most negative example that we've been able to come up with. We haven't found anything more negative than that. But if there are other line arrangements that have no simple crossings, we're hoping that they would give us maybe even a more negative value. But what we can do, this is an argument that's similar to the one over the reals, actually. Well, I don't have time to explain it, but it would be interesting to know if the linear h constant actually achieves -4, or if this is the best you can do, and we don't know. So an open question would be, compute this. But we have no, this is all that we know so far. We have no ideas how to do any better than this. Well, I should stop now. I'm just a little over.